Yeah. Leave me to my torture over here. Mosh, can you check the YouTube channel real quick just to make sure we're live?
What are you guys' opinion of the deletion act that just passed 2 weeks ago?
The what
I'm
now?
not aware of it.
The what?
Oh, the one where you can delete your data for California?
Yeah, and
I haven't read it yet, so I don't have a form committed.
I think California is pretty good with privacy overall relative to the rest of the country. They actually have like a Department of Technology, I think, that was formed last year or something. So, I don't know. I mean, I'm generally in favor, though, of anything that gives people a little bit more control of their data, but at the same time, when you agree, you're agreeing to kind of, like, I know no one reads it, but you are agreeing to their terms, and their terms do. So, obviously, it needs regulation, but...
yes, you're live.
All right, cool.
Thank you, Mosh.
My only fear is regulations that favor the already kind of quasi-monopolized state of tech, because sometimes there can be required infrastructure that acts as a barrier to entry for competition. But I don't know. I don't know if that qualifies in that realm, but it is. I say I'm not a politician, and part of it is because I let people whose job it is, I just vote, and I call it good with that, you know what I mean?
yeah, but
just
at the same time,
Michael.
Well, hold on, I think someone's speaking.
letting politicians decide everything, they
Yes.
know everything.
Yeah,
So
I mean, if
having experts come in.
right, if you've seen the committees, I guess they hold with like some of the tech, CEOs and whatever, and you have senators asking, Meta executives about Twitter, it is concerning. So it's definitely.
Well, I mean, we know that these politicians are mostly just acting. They're just trying to get screen time.
Yeah.
It's mostly the fact that they're getting most of their information from big corporations that is my concern. We don't really have that much like you can go to academics that specialize in like sustainability or something like that. And there doesn't seem to be like that much of a niche when it comes to tech.
There's a lot of lobbying that goes into the process right now, for sure.
Did the computer? No, it didn't. Okay, perfect.
But what was I going to say? Oh yeah, like the whole thing about I guess whatever they were doing around TikTok, it was really obvious to me, at least. I think that they were just favoring because the shorts and the whatever the reels. I mean, that's just TikTok. So the reason that there should. Mosh, would you be able to?
Sorry,
it's all good.
Disable the robot quick.
It was kind of obvious to me that they were just favoring American tech companies, but at the same time, when you have malicious actors, I think you can choose a lesser of two evils. It's a really, there's a lot to dig into. There's a lot to pull apart, but it is very clear that there needs to be some sort of educated voice in our government, which is why, though, I think when we talk about state level stuff, I find California does a better job than, though we have a lot of the industry is like here, so I think that plays a role, but I don't know, I can't speak directly to anything exactly, but yeah, definitely do need some rules to put down. There's case after case you can talk about some overreach. Yeah?
I like to compare what California is doing to the EU, because the EU basically got Apple to change the charging ports on the new iPhone.
They're doing so much better.
Yeah, honestly, I think I would say that the EU uses a heavier hand, but which can be a detriment to growth, but at the same time, there is the whole balance of maintaining sustainable growth and having regulation act on behalf of consumers. So the USB-C thing like enforcing standardization, I'm okay with that sort of thing. Like that just makes sense to me. That it's frankly it's just part of the Apple business model to sell you all the ends and odds, from my perspective.
A lot of Europe's regulations are actually Eurocentric.
Yeah.
When it comes to especially food, they say, oh, it's cancerous, no, it is not. There's no actual proven fact. They just did like one test that said, well, we can't determine anything, so they just made it illegal to have certain like food dyes in them.
I see.
And then there's also the huge part of those regulations is also some people can be allergic to it.
Right.
And so they also ban the may be allergic to it kind of thing. It's like
Sure.
banning peanut butter because people might be allergic.
Yeah, yeah, they definitely can get heavy-handed, which is why I'm hesitant to like blanket support EU policy, especially because like the people who put the GDPR, I think it was, in place, I don't think most of them actually knew what they were passing, but it was lucky that it was written well enough that the interruption to service and everything wasn't so dramatic that industry couldn't recover and compensate for that sort of thing. But yeah, I mean, definitely, if you feel strongly about something and you've really looked into it, our congressman is pretty good about getting back to you. Huh?
Which one?
Ami Bera.
Oh, yeah.
Yeah.
Ami's pretty nice.
Yeah.
He answers phone calls every now and
He's
then.
all right. You know,
He's pretty cool.
definitely tries to do outreach to his constituency.
Other congressperson.
That's at a federal level, though. I don't even know who our district representative is for the state, frankly. But
It was
Ken Cooley or
Kevin
something?
McCarthy, but he stepped down because he's running for mayor.
Gotcha.
So currently we have no representative.
Gotcha. Well, in any case, that is a great, actually, it is a great conversation, and I think we could actually kind of continue that maybe for next meeting. I was thinking we could do something a little bit like current events. It sounds like there is some interest to that, so maybe if anybody has any suggestions or anything they want to talk about, for sure, definitely something to look into that we can talk about next meeting. But I mean, I didn't want to cut anyone off. Does anyone want to add anything to that? No? Okay. Well, so in any case, I'm just going to roll into some announcements. If you weren't able to sign in, we're going to hopefully get that resolved by the end of the meeting. And then, does anybody have any announcements of their own? Any questions, comments so far? Sure. Yeah, Mosh? Yeah, I'll come back to you. So I did want to talk about one thing in. All right.
Okay. If you guys want to, there's this event going on the
Excuse me.
in front of the bookstore at the Cerna Plaza. It's like a multicultural concert. Here, I'll pass you guys the flyer. You can take a photo of it. But
We can look at it.
if you guys are in 177, you can get extra credit 1%. You just gotta make
This is for people who are in Dr. Chindella's data analytics class.
yeah.
Please turn on. Perfect.
Just make sure to check your canvas because it displays all the instructions on what to do when you send him the confirmation that you attended this event. But anyways, pass this along to your friends and take a photo if you like.
Yeah,
It's posted in the Discord.
if anybody's interested. Great. Cool. So yeah, check that out if you're interested. Additionally, not additionally. Just pivoting a little bit. And if you're interested, feel free to. We can cover it towards the end of the meeting as well. But I do want to talk about constituency a little bit, voting rights and all that. It's been great that we've had so many members actually participate this semester. And in addition, definitely looking to continue the policy of requiring only a single meeting to be a member of the club. However, there is a concern that I have that we have what is a 1/3 requirement to meet quorum, which is what is required before we do any like official business, like voting and all that. And as we push towards 60 members, we will need 20 people then at least. We're not there yet, but it could be by the end of the semester when we are going to actually hold elections, that we will need 20 people. So if there's any sort of amendment or any sort of idea that anyone in membership has that might be able to solve a problem in case we aren't able to meet quorum, I have some idea, but it's kind of
It's 3 o'clock.
I wouldn't say that it's the best idea, so if anybody has any idea of how to possibly solve the voting issue, yeah, feel free to bring it up. But if no one's really super concerned about it now, if membership isn't really concerned about it, then it might just be an issue we kick down the road. Next, right. So something I did want to bring up, we don't really have to worry about it, I think, even this semester, but I know there is already this robotics project that's going on. That is, though, now asking for members with a little bit more experience. There will, though, be an expo in April, early April, for the where the ECS college wants the clubs to come out and present a project. And they mentioned interactability is key, so something you can interact with. So if anybody has any ideas for what that could be, and ideally it's something that anybody could participate in, feel free to bring it up. And yeah, I think I have some ideas too, but just again wanted to bring it up now so that y'all can start thinking about it. And with that, we're good.
All right, without further ado, let's welcome David Castrejon.
Let's take it a little faster there. One camera, one good. Yep. Oh, your slides are up here already, by the way.
Yeah, just in case there's a question about it, I have like some notes on something here.
For sure.
Careful of cables. It made it an obstacle for you. Keep going with those.
Oh, nice. Yeah, it is right there. Can you hear me, by the way? Yeah?
Yeah.
Awesome. All right, so just go ahead and start.
Yeah.
Cool. Sounds good. Okay. All right, so hi, everybody. My name is David Castrejon. I'm a student here. I'm a senior, and I do computer science and applied mathematics, and I do plan to go to graduate school as soon as I graduate in the spring, hopefully. This past summer, I was part of something that was called a NSF REU. And what that stands for is the National Science Foundation Research Experience for Undergraduates. And what that is, you apply, and all you need is one more semester by the time of completion of the program, and then you go out to some university here in the US, and you do research with a small cohort under a faculty at that university. And you get to choose which projects you want to do, so you can apply to many different of these REUs and pick the one that best aligns with your interest. In my case, I applied and I got into this one here, which was at CSU Northridge, and there we did a lot of data science stuff, a lot of machine learning, and my project in particular was California wildfire risk prediction and visualization. My other researchers that I did the program with are obviously not here today. They're from other universities, so I'll mention them, which is Dennis Osmak, he's from University of Austin, Texas, and then also Connor Wang, which is from UCLA. And then below is the faculty and the other graduate mentor as well. Okay, so now I will, I'll take questions at the end, thank you. Now I'll go ahead and just talk about what we did, why we did it, and how we did it. So motivation. California is the most fire-prone state in the entire United States. Back in, I believe it was 2020, around 2020, 2018, we had a massive fire, the Dixie Fire, and that burned an enormous amount of area in Northern California. My family's home was almost completely taken down within just a few acres, so it affects a lot of different people from everywhere in the state. And the wildfire costs of damage were estimated to be around $148 billion just in 2018 alone. And that takes a lot of our budget. That has a major effect on the environment, and it is worth looking into for ways that we can use data science and machine learning to help mitigate that a little bit. So the goals of our project was to train some machine learning models to best predict wildfire risk in California. And the way that we did that, we used NASA remote sensing data from their satellites, and we trained our models, and we went ahead and see if we can predict the risk of them. There is also existing research, which we kind of based our own research upon. So we took the previous literature, which I will go into in just a moment, and I will explain what they did and how we expanded upon it. So the previous literature was California wildfire prediction using machine learning. It was done by our faculty supervisor, and their goal was very similar. They wanted to use machine learning to help predict wildfire risk using the same remote sensing data. I take that back, not the same remote sensing data, just some remote sensing data, not the same one. So what they did 5 machine learning models, and they trained those models on just a very short time period of about 2 years worth of data. The data sets are right up there. Some of them are similar to the ones that we use, so I'll go ahead and gloss over that at the moment. But just in general, they were things such as vegetation, surface temperature, etc. So they did that on a very short time span of about 2 years. And our goal, which I will go into right now, was to go ahead and, wait, is it going? Hold on, slide 6. There we go. So our goal was to expand upon that and not do it just on 2 years, but about 10 years worth of data. So we instead expanded upon the length and expanded their data by a vast amount and trained our models on that instead to see if we can improve it or find any other kind of insights as well. On top of that, our goal was also to perhaps visualize this complex geospatial data set, because there's lots of different geospatial data sets like temperature, vegetation, wind, precipitation, etc. And we don't really have a lot of ways to see it or to get information and insights from it. So that was another part of our project, which is given in the second point there, to help educate the general public and create new ways to visualize that data. So our data sets, which are the ones that are right here, we had enhanced vegetation index, surface temperature, thermal anomalies, wind speed, burned area, and fire records. So we can just see here that this is representing the spatial resolution from the images that we took, the temporal, so how frequently was our data sampled, and a bunch of other information such as size and where it came from. But I'll go into each of these in just a moment here. All right, so the first one, EVI, stands for Enhanced Vegetation Index. We received these from the NASA Appears tool, which, like I mentioned, is just remote sensing data from their satellites. And this data was taken at a 16-day temporal frequency, meaning that when we download the data from around 2013 to 2023, we get files that are formatted in such a way that every single file, it represents a single set of data every 16 days. And that is the temporal frequency there. Now, the temporal frequency was not the same amongst all of our data sets. Some of them came daily, some of them came 16-day. So we needed a way to kind of mesh them together so we can train our models based off of that data and analyze them in a nice way. So we had to use interpolation, which is that point there, interpolating to daily frequency. What we did there is we used linear interpolation to go ahead and take that 16-day frequency and essentially create files for every single day in between using that linear interpolation. You take 2 points, make an equation between them, and every point along the way, that's where your new data points would be for each of those days for every pixel all throughout California. It was a lot of data. I'll get into the size of that in just a moment. And as you can see here, this is one visualization that we did of that. Green being higher vegetation and red being lower vegetation. As you can see there in the desert, it's pretty red. There's not much going on there. In Northern California, there is a lot more vegetation, so it's a bit more green. All right, so burned area. Burned area taken from the same data set, same data source, the NASA satellites. This represents exactly what it sounds like. Burned area, just area that has been burned within the last 10 years. And the reason why we needed this is because for every single pixel, it represents a 500 by 500 meters area of California. Now that is a lot of data, and we cannot go through all of that efficiently within our 2-month time span. In addition, not all of it is relevant. If there is an area in California that has not been burned in the last, 40 years, it's probably not really relevant to train our model to try and predict wildfires based off of that data. We want data that from an area that has been burned before recently, so we can train it on areas that are more frequent to fire burning and maybe get better estimations from our models. So that's why we extracted the burned area here, and we use it as a mask to overlay it over all of our other data sets, which is exactly what that looks like there. So right here is all the areas within California that have roughly been burned within the last 10 years, and we laid that over all of our other data sets to get the essential pieces of data points. Thermal anomalies were another one. We went ahead and took this one, and every single little red spot there, like it seems, is just a thermal anomaly. Could be a fire, could be lightning strike, anything. So we got this one. This one was a daily temporal frequency, so it was already ready for us. There's no interpolation needed. It was just kind of ready to go. And lastly, I believe, is the land surface temperature. Self-explanatory. This one was actually taken at a 1 kilometer by 1 kilometer spatial frequency. The other ones were 500, meaning that this one, for every single file, was 4 times the size of all the other ones, which kind of presents a problem, because if you want to overlay all the data and get insights from it, you need them to be of the same format to get valuable insights. So for this one, what we did, we took every single file and we split it into 4, like a little crosshair, and where every single little square would be the same spatial resolution as the other data sets, being 500 by 500, 500 by 500, etc. for each of these files throughout the 10 years. Do you have a quick question?
An alternative would have been to go the other way and take the 4 and maybe average their values.
Potentially.
Was there a reason that
Yeah, potentially. But the thing about that is the other data was much bigger size than just this data set. So it was just a lot quicker just to change this one in particular versus the other, 3 data sets that are a lot bigger in size. So yeah, so it was just more efficient this way. But that could have also been a good option too. Yeah, and then as we can see here, the color scale: red, higher temperature; blue, lower temperature. Okay, wind data. This one was actually a bit interesting because it's not like the other ones. There's a lot of different heterogeneous data sets that were used here. This one in particular was not taken from remote sensing data from satellites. This was taken from weather stations throughout California. And each of those weather stations gives their observations to a data set called the GHCND, stands for the Global Historical Climatology Daily Network. It's a long name, but basically just weather observations of all different kinds: snow, wind, temperature, etc. We wanted wind specifically. So we took that data, and that data actually had data from all the way back in like 1770 something to present. I'm sure 1770 something observations are not going to be that accurate or useful. I don't know why they're there, but we didn't care. We only used the more recent ones, which actually were pretty useful. Another thing about this is a global data set, meaning this wasn't just for California. We extracted the data set for California, but this involved the entire world. So this entire data set was just CSV files that were over like hundreds of gigabytes in size. So we had to extract the California data sets just based off longitude and latitude for those points that are just inside California. It was a bit tricky, but I'll go into how we did it in just a moment. Also, before I do that, this is a little small visualization of what each, where each of the weather stations are for like Northern California. There's more in Southern. And this is just a visualization of how we visualized the wind data once we extracted it, with pink being a higher wind speed and light blue being a lower wind speed. But I'll get into that in just a moment. Okay, cool. So this is how we found the exact data points for California. What we did is we went ahead and used the latitude, longitude, laid it over our mask with our with a different file, which represented each latitude, longitude point of California. And we parsed the entire data set just to get the ones from California for the specific dates that we wanted, from 2013 to 2023. One other small thing that I just forgot to mention, I'll mention it right now. If you look at the wind stations, or the weather stations, there is not a data point for every single pixel of California like the other ones, like a satellite image, where you have a measurement for every single pixel. Here we have weather stations, which it's a bit trickier to work with, because how are we going to correlate that with the other data sets where they do have a point for every single 5 by 500 meter area in California? And I just wanted to mention that really quick before I go into the next slide, because that's what I put on this next slide here. So with that in mind, what we had to do is for each of those weather stations, we had to use something called the Haversine formula. So what we did is for every single weather station, we took the closest wind observation to every single point within our file of California. So I'll go deeper into that right now. So if you look here we have a data point for every single point in California. There we go. What we did is we went through every single pixel of this image and at every point calculated the closest wind observation to that point using this formula that I have here on this slide. We had to use this formula because we had to take into account the curvature of the Earth. If you just took the distance as the bird flies, it would lead to some miscalculations. So we had to use this formula for every single point to find the closest wind observation, and that's how we got the average of those data points there. And then from there, we again had to use more interpolation and get data points for every single day for those 10 years of California. That was a bit more complex than the other ones. That one took about like 2 weeks to do right there. Okay, and then this one's really quick. It's just fire records of all the past fire records from CAL FIRE. So these are specific. We use these specifically because we wanted wildfire data points. And there's lots of different types of fires. There's like lightning, man-made fire, etc. But we're particularly interested in wildfires. So we took this data set and it has all the wildfires from California for the past 10 years. Okay, I believe that was the last one. Yeah, okay, that was the last one. So what we did is we took all those different things and we put them into one CSV file where every single row represents one latitude longitude point in California for a specific day. And each of these columns here, as you can see, have each of those different data sets in every single row for that point, for that day in California. And this entire file, when compressed, was 7.3 gigabytes long. Yeah, it was a lot. It was a lot. Yeah, it was a lot. Every single data set actually had over 20 billion data points for every one of those data sets that I just mentioned. So total, that's over 100 billion different data points that were needed to be organized, structured, and then fed to our models. So yeah, it was big data. Okay, so moving on from those data sets, I'll come back to them later in the machine learning portion. I just want to get into right now the visualization portion of our project. The visualization of these complex data sets and seeing them in maybe a different manner that hasn't quite been seen before. So we use a 3D computer graphics software called Blender. And I will go into what these visualizations look like in a second using this software. Is it white? Yeah, that's just white. Okay, so I don't know why it's simply white. There we go, there we go. Yeah, and it's also fuzzy. Didn't anticipate that. On my computer, it's like crystal clear, but you can kind of get the idea. I also posted these somewhere else. I'll share where they're at in a second.
They're still kind of blurry there too.
Never mind, it's fine. Okay, anyway, so I wish it were clearer, but if you can imagine like a 4K image of this. Yeah, what these are, as you can kind of see down here, it's like little tiny pillars pointing up. Green pillars are taller than the smaller red pillars. With smaller red pillars represents a low measurement, tall green pillar represents a high measurement. This is specifically for EVI, Enhanced Vegetation Index. So this is a health of vegetation throughout California for one day of California somewhere in between 2013 and 2023. I just picked a random day just to show you guys to see kind of what it would look like. And I'm pretty sure the next ones are also going to be a little fuzzy too. Let's find out. Is it fuzzy? Yeah. It's fuzzy. Okay. Well, hopefully the videos will. Let me try something really quick. Skip verification.
Your diagram looks like the whole state got swallowed up by the Pacific Ocean.
It does. It does. Now, will this go? It will not. Okay, that is totally fine. We're just going to ignore that for now. Where is the presentation slide? Can you bring me back to that? Oh, I found it. Never mind. All right, we're good. Well, there's videos that we have which are pretty cool that I really wanted to get into. Unfortunately, the YouTube video will not play. So yeah, no, I can go into it later. It's okay. Yeah, I'll go into it later. I have links to them.
And that looks like it's Ice Age the Meltdown.
It does. It does. So this one right here was wind. I know it looks really fuzzy, but online we do have videos of the animations, which is what I really hoped I'll be able to get into. What this would have looked like is, so this image right here is just one day somewhere between 2013 to 2023 of wind data. And just like the last slide here, this is same thing, but this would be for land surface temperature. What we did is we took every single one of these kind of files for every single day, for every data set, and we lined them up perfectly into one animation so you can see how the change in temperature, how the change in vegetation, etc., whatever data set you want, how it changes every single day throughout the years. So it's actually really cool because you'll see them kind of follow the exact seasons. For land surface temperature, this would have been super, super high in the summer, and then you see it kind of die down in the winter, and every single frame represents one day in California. Again, I have YouTube links to this. I'll put them somewhere so you guys can see it. It's pretty cool. Unfortunately, it didn't go today. Wish it did, but it's all good. All right, so we'll just get on to the machine learning portion then. So the machine learning, what we did is we tested a few different machine learning models to see which one would best predict the California wildfire risk. So we just chose these, and I highlighted the one there that did the best, just to give you an idea in advance. It was the multi-layer perceptron model, which changes weights between decision-making nodes. And I'll get into it a little bit more right here in this next slide, if it goes. There we go. Okay, so there were a few restrictions that we ran into when we began training our models. So first one, just first and foremost, the data sets that we use do not encompass every single factor that goes into a wildfire. There's a human factor. There's accidents, there's lightning, there's proximity to humans. So I'm sure an area that has, an area that's never visited by humans probably has less fire than the ones that do. So that was one factor amongst a few other limitations. One other limitation was that we had a humongous data set. And the points that actually indicated a fire, well, they're a lot less than the points that indicated no fire. So there's a ratio of around 1 to 32,000 fire to no fire data points. And that, spells a little bit of trouble when you feed it to a model. Because when you feed it to a model, what's going to happen if you have a bad ratio like that, it might be pretty good at predicting where there's no fire, but where there is a fire, it's going to be pretty bad. So what we had to do is we had to go into a bit of sampling and oversampling techniques to go ahead and fix that imbalanced data. In addition, we unfortunately were only able to train off of 1 year's worth of that data simply because it would have taken a long time to do so. Not that we couldn't do the whole 10 years, we really wanted to, but since this program was only 2 months long and we began this in around the last 2-ish weeks of the program, after we did all the pre-processing, we just didn't have time. So we can see here that the runtime just was insane. It was like over 2 days just for the 1 year that we decided to do. So these are some of the oversampling algorithms that we tested. A few of them are listed here, but the best one was the synthetic minority oversampling technique. Basically, you just oversample the minority class, which was the fire data. And then you undersample the other majority class, which was the no fire data. We tested a bunch of other oversampling, undersampling techniques, but this one we just found to be the best. The other ones are mentioned there, and they're acronyms for a bunch of long names, so I don't remember the names of those acronyms, so we're just going to move on from there. The most important thing, SMOTE, that one worked the best. We also tested a few different ratios as well, a few different ratios of the fire to no fire data. We tested the 10-to-1 ratio, 4-to-1, 2-to-1, 1-to-1, etc. And we found that the 2-to-1 ended up working the best. Okay, putting that all together, testing all these different things, all these different variables, we found, like I mentioned, the multi-layer perceptron neural network to work the best. It did predict with a 82.7% accuracy of whether there was a fire or no fire. And like I mentioned here, these are just the different things that we use to get this model to work, the SMOTE, the 1-to-2 ratio. We also use sklearn to go ahead and implement this as well. And we tuned the hyperparameters using grid search CSV. And I will go ahead and 3 to 4 hours. Yeah, it took 3 to 4 hours to run the model. Took a very, very long time to get these testing points. Okay, and then here's a confusion matrix. I don't know if you guys have seen a confusion matrix before. If you haven't, all it represents, top left, we are going to have the true negatives, meaning that it predicted that there was no fire correctly. Bottom right, you're going to have the true positives, meaning that it predicted that there was a fire correctly. Top right and bottom left represent the false positives and the false negatives. Obviously, that just means that false positive, it said there was a fire, there was no fire. False negative, it said there was, no, false negative, meaning that it said that there was no fire and there actually was a fire. And this is just an example of the confusion matrix, but we had an 82.7% accuracy there. One thing that we did notice is although the accuracy was decent, it wasn't bad, we wish we could have trained on more of our data, but the precision was extremely low. It was a very low precision of like 0.18%, which is pretty bad. But like I mentioned, there's a few different reasons why that could be, a lot of different factors. One of them in particular was that the regions that we were testing, the training data versus the testing data, they're so close in proximity that also could have affected the precision rate as well. Maybe we could have tested on specific regions only versus the entirety of California. That might have also changed the results a little bit more. But in conclusion, we created a few different 3D graphics visualizations with Blender. I'll put the links to those so you can look at them. And we hope that by exploring these different visualization methods that we can better educate everybody and see the things that are going on within our Earth. In fact, we decided to extend this research, and now with the LSAMP program here at Sacramento State, we're going and seeing how we can visualize, and predict the effects of Amazon rainforest deforestation using a similar type of concept. But luckily, we have a whole year to do that one, so hopefully we'll find some pretty good data, some pretty good outcomes with that research. And like I mentioned here, we have the just mentioning the imbalance data for the fire model, 1 to 32,000 on average, which is a pretty big oversample or pretty big minority to majority class. And that's what the image represents here. Just an example of what that might look like, where the orange is your minority class and the blue is the majority class. And you can just clearly see how there's a big difference in that ratio right there. Future work, maybe put more data sets is another thing. Speed up the runtime. We did not use GPUs. We did not use GPUs mainly because most of us, when we went into the program, we did not know how to use CUDA. And given our 2-month time span there, that would have been a lot to do all this and learn CUDA and implement all these different things. We were all learning, and that's the main point of this program, to take undergraduates and get them interested in research. So now we know. Next time, use CUDA. For Amazon, we're going to use CUDA, which utilizes GPUs to go ahead and run these processes. It makes it extremely fast, way faster than a CPU if you were to run these same things. And also maybe publish a web application. That'd be pretty cool too. A web application, a website where you can go ahead and look at all this data, see the visualizations, and see the changes in these data sets over time. That's another potential area of future research as well. I'm gonna be honest, I don't know why that confusion matrix is there. We made this slide thing while we were in the program, so I'm gonna just gloss over that. And so acknowledgements, this is funded by NSF, National Science Foundation. This is the grant code right there. We did it at CSU Northridge, and we're just acknowledging Dr. Mario. He was a geography professor there, I believe, and he helped us out with like figuring out what data sets would be most useful, etc. There's referencing the data sets and where we got them, and the previous research that we expanded upon from our faculty advisor. And I believe that is that for that portion, and I can go ahead and take questions. Thank you all for listening. Let's go with you.
Would you also do data visualizations on like how many cars were burnt or how many bodies were found?
I don't know about that. That's an interesting one. At the moment, I'm not sure how you'd go about that, but maybe someone else can look into that.
Do you think you might do something, another project similar to what you did here by actually doing it on Hawaii, especially after what happened in Maui?
Yeah, that's another cool thing you could do. The good thing about these kind of projects is that if you make the code general and you allow it to be used for other geographic locations like the Amazon, like I mentioned, you can go ahead and apply it to any region of wherever you want in the world, because these satellites orbit all throughout the world. They take data very frequently, so you can go ahead and find out lots of useful information, which is another goal that we have, to publish the code and give it to everybody for them to use. Yeah.
What other data sets do you want to do in the future and opportunities?
One of the ones that I personally would have really loved to incorporate here is population. Because like I mentioned, if there's an area that is not frequently visited by humans, just most likely that probably wouldn't get burned as much. But that's another restriction with predicting wildfires in general, is just that there's so many different factors, especially, a lot of it's accidents as well, which is really hard to predict just with a neural network to predict an accident. So I would have loved to use population. Maybe we would also have loved to use something more about like the moisture of the vegetation that was there. That might have also been nice. And there's a plethora of other data sets that could be used in future research as well. So yeah, definitely incorporating more data sets would be really helpful. Yeah. Any others? Yeah? Oh, do you have, wait. Whichever one.
With the immersion of the formerly dead lake, would you think that there will be a great difference in your data sets to come?
That's a good question. I will be honest, I don't know what that dead lake thing means.
In Southern California, one of the formerly dead lakes re-emerged during the rainstorms of last year.
Oh, really?
That's Central California. That's, I think, the Tulare Lake.
Oh, wow.
Tulare Lake, that's in Central California, though, because that's in the San Joaquin Valley. So, kind of in Southern California, but not even close. It's like in the middle where Fresno County is, and Kings County, and Kerr County as well.
Okay.
So, still in Central California.
What I would probably say is that that's a major geographic event, having a whole entire lake, become re-emerged. So let's say there's, I don't know, like a giant earthquake and the whole city is gone, or like that happens where a whole lake emerges. That would probably be time to maybe retrain your model, because now you're kind of testing it on a different Earth essentially. There wasn't a lake there before. The climate's going to change around where that lake was, so maybe certain events will be shifted as well. So you might have to do separate things if a major geographical event like that were to happen as well. Yeah.
Would it also be harder to track down data for like wildfires if it was if it was caused by war, like it was a war-torn country with a bunch of dead bodies and probably a bunch of nuclear waste because, if they called in a nuclear strike and... Yeah, well, I was trying to be on topic. I just wanted to reference if casualties of war would have also affected data analysis.
Potentially, but that's another event that is kind of outside of the realm of, it falls into the realm of unpredictability, and that's not something that you can really predict well with the machine learning model. So, yeah.
Were there any data sets where you had a hard time getting a hold of due to bureaucracy?
Yes, that's actually a really good question. Oh my God, literally about 3 weeks of our time for the first part of the program was spent just downloading off of Portuguese websites and things that would not translate over, and we had to use this API that had no documentation, and it was a pain. It was a humongous pain. That is one thing that I also wish I put in the slides as well. There is a severe lack of accessibility when it comes to these environmental data sets, which I really hope that in the future we have maybe a more centralized place to publish these things, or maybe if researchers just publish their data a bit more and make it more accessible. I mean, even NASA we had a little bit of a hard time reading the documentation, looking through it, getting the API to work. So yeah, there's a lot of work that can be done getting these data sets more accessible to the public for sure. Yeah.
I have a question. So could you speak a little bit about how you heard the opportunity and maybe what the process was getting involved?
Sure. If you don't mind, I'll speak about that in a second. There was one somewhat major thing I just forgot to mention, but I will touch on that right after. So as soon as we finished this research with about 72 hours left, we were done. We had all the data. We made our little poster and everything. We presented. But then we found out that there was a conference, like the next Monday. We found out on like a Thursday or Friday that there was a conference that we could submit a paper to. So our group, 3 undergraduates who knew zero to very little LaTeX, we spent like 13 hours a day crafting this research paper. And luckily it did get published. It got published at the ICMLA 2023 conference, International Conference for Machine Learning and Applications in Florida. And now we're invited to go speak at, well, not go speak, we're invited to go present our poster at that Florida conference, and we can see like the latest machine learning research, etc. I just wanted to touch on that really quick, as he mentioned opportunities, how you can get into this program. This is one of those things that can happen from this program. You can definitely write a research paper. You have the chance to get published. So if any of you have more than one semester remaining after this coming summer, I highly encourage any of you to apply to many different RUs, throughout the US. Whichever one you find that best fits your research goals. Or if you just want to go to one and have fun, totally cool. It's a great experience. Yeah, so now I'll get into like what I did to get there. Honestly, I heard about it through Professor Fitzgerald, sorry. He's the stats professor, I'm sure lots of you guys know. I took his 129 class here, big data, and he sent it in our Discord, this opportunity at CSUN. I didn't even know what an REU was at the time. I just was really looking for internships, so I put my application through. Standard application, I think it was like a resume, cover letter, I believe 2 references if I'm not mistaken, and that was it. I just heard that we'd be doing research and it sounded really cool, so I was like, all right, yeah, I'll do it. And then they got back to me, and I had one interview. And in that interview, it was a bit of a mix of behavioral and technical. Behavioral as in they asked general questions about like who I am, what I want to do, what I have done academically, but that was more brief. The main portion was they really deep dived on the projects that I had listed on the resume. And each of those projects, ironically, came from his class that I was taking that semester, Dr. Fitzgerald's big data class. We had a machine learning project that involved IRS tax data analysis. We had another project, which was probably the main contributor to me getting this thing, was we had a project using that same global historical data set, and we did analysis on that as well. And that's actually what the interviewer deep dived into, because at the time I didn't know, but this project involves a lot of geospatial data sets. So she really loved that, and we talked about that for a while. I basically laid out every single step of what was done in that program, that project, why I did those steps, etc. And yeah, then this whole thing happened, and I went. And when you go to this And when you go to this program, it's a 2-month program. You have the option to commute if it's close. So I know Davis has one as well. I have a friend who went to their REU for civil engineering. So they have them for other fields other than just computer science, like biology, civil engineering, etc. So you go for 2 months, you can commute or you can stay there, and you get paid for it too. We got paid a decent stipend. I got to do a few fun things with that little stipend. And yeah, it was a great time. So, question?
With this internship, you said that your colleagues were at other schools?
Yeah.
Did you work remote or did you live with them?
No, we go there and we lived there. We lived in the CSUN dorms. And I shared a 2-bedroom apartment with 4 people, and I had a roommate from Texas who just slept like 4 feet away from me that I just met. It was a great time.
Northridge?
Huh? Yeah, CSU Northridge, so it's in LA. It's like northern LA.
Did you go for the summer or?
Yeah, this is during the summer. Yeah, this past summer. From June to the end of July. Yeah. Question?
Did they pay for housing?
Yeah, all paid. You get paid a stipend. I'll just let you guys know. I got $5,000 bucks. That was pretty cool. And they also took care of all the housing. Did not come out of my own stipend. So I just got to hang out, do research. It was pretty cool. Yeah. Exactly. Exactly. Yeah. So it was actually really cool. It was really cool. As far as what it looks like when you're there, I mean, it's not like you're there and someone's like watching over you 24/7 or nothing like that. It really mimics what real research is like, where in a sense nobody watches over your shoulder. It's kind of up to you. You do all the work and then you present your findings. You all come together, talk about it, and you move forward from where you're at. So when we would go, we would meet every morning at 9 a.m. and we would do a 1-hour training. It's like 1 to 1.5 hours roughly. And we would learn like new technologies. We would learn new things in computer science, just tools to help us do research. After that 1 hour, hour and a half, we were free. We could go wherever we wanted on campus. We could do whatever we want. No one checked in on us. And then we just came back the next day, and hopefully we did work. So, I mean, it really is up to you. Of course, we had guidance. I mean, we could always contact our professor. She was always there in the room if we needed help or whatever. But as far as like anyone keeping track of you, like you could do whatever you want, which was really fun. It was really nice to do that. So yeah, it really mimics research where no one's going to watch over your shoulder. And it was a great experience, you know, because going into grad school, it gave me a really good feel of what that actually will be like. So I'm really happy that they did it in that fashion. So yeah.
Do you mind going to the first slide again?
The very first one? Yeah.
With all the QR code, just to make sure we got it.
Yeah, for sure.
So we had an abundance of food, and we need everyone to sign in, because if Sol looks at me and says you only had 5 people sign in and you bought $300 worth of food, they're going to give me on a book. So if you wouldn't mind signing into this QR code real quick, it's also posted in the Discord so that we can take attendance. One more question. Yeah, go for it. I just need this up so people.
So I know you talked a little bit about it already, but was it mostly other computer science people, math majors? Like, what was the work environment kind of like?
Yeah. Well, the main goal of the program was to get undergraduates interested in research in general. So you were able to apply from, a few different backgrounds. You could have a physics degree, you could have a math degree, a computer science degree, statistics, that one also works too. This one was specifically computer science. So all of us there happened to be data science or computer science majors. But you can technically apply to whichever one you want. So if you feel that you have experience or projects that fits into a different field, even if your major is different, you can still apply, and maybe you'll get in. The goal is to just take, like I mentioned, undergraduates and get them interested. So you can apply for a bunch of different things from many different backgrounds. But of course, if you have a major that aligns with the one you're going for, that would definitely help a bit too. So all the people that I were with, they were all computer science or data science. Majority of them were actually like freshmen or sophomore, really. I was only one of 2 seniors in that whole entire cohort. And there was I believe 10 people, 11 people-ish, so something like that, around that number, 10, 11. And only one student was actually from the university. Everyone else was from, somewhere else. So, me, Sacramento, and then like Texas, Connecticut. There was another one, Nathan, who's a cool dude. So from many different backgrounds. So it was really neat to see. Yeah.
Cool.
Yeah. Any other questions? Yeah.
Sorry, what was the program called again?
Did everybody sign in so I can change the slide really quick? Yeah. Okay, cool. This is called an NSF REU. REU standing for Research Experience for Undergraduates. If you just look up NSF REU, you'll find tons of information about it, how to apply, all that good stuff. Just look up those little key acronyms, and you'll see everything there. And like I mentioned, they're throughout the U.S., many different universities. So you can apply to as many as you like, and that's actually encouraged because the acceptance rate for these is, I didn't know, but it was actually pretty low. It's around like 2% or something like that, or 1% even for some of them. Like Berkeley, I'm sure that one's probably like super low. Go ahead and apply to a bunch of them if you do want to go to maximize your chances. Yeah. Any other questions? Yeah. Oh, sorry. You go ahead. Go ahead. Yeah. Sure.
How is the application process? Was every single application going to be different, or are they all centralized as in like audit errors?
That's a really good question. From what I remember, and I'm gonna be honest, I only applied to this one because I didn't know what an REU was. I didn't even know that Davis had some, etc. From what I remember, it didn't feel like it was a centralized thing that you could just, check off whichever universities. Mainly because they're ran by different professors, they have different projects, so it's kind of up to that institution if they want to take these students. So you will have to probably do slightly different things for every single one. But generally, if you're applying for all computer science ones, generally it'll be the same. So you can do the same resume, etc.
I actually signed up for one of these recently. So you can find them on Handshake. I'm gonna move over there so I don't yell.
So you can actually find these on Handshake if you just look up NSF. I was trying to get into some cybersecurity ones. By the way, if you guys are trying to get into some cybersecurity ones, they're really trying to get people to join some of their research projects, but they're, like you said, they're very, very selective. So they're still trying to find more people to get in, but they want a lot of good candidates. They also go for very passionate candidates. So if you don't know anything about the topic, if you're very passionate and show that or if you can show through your resume that you submit that you are extremely passionate about it, you also have a good chance of getting into one of these programs if you know nothing about it. Would you say that would be?
I would also agree with that too.
Yeah.
It's almost counterintuitive that having a bunch of experience, you might think like, oh my God, I'm almost guaranteed to get into this. I have like 10 years of research experience or whatever. It's almost counterintuitive because the goal of the program is to get people who kind of in a sense don't have a huge background in research specifically and get them interested in it. So I mean, for me personally, I had 0 internships at the time. I believe I was only a tutor. I was only a math tutor here. So there is some experience, but you know, it's definitely not as much compared to probably some of the other people there who applied as well. But yeah, so it's kind of ironic that like maybe a little bit less. Don't be don't be intimidated. Still apply. You know, you might still get in, for sure. One last thing I want to mention as well. When you're here because they want to get you interested in research, that is what you do in graduate school. You mainly do a lot of research. So within the program as well, they had so many workshops like helping you with like statements of purpose, applications, informing you about the different grad programs. We even went to go visit University of Southern California. We presented at University of Southern California amongst a bunch of other kind of really cool workshops too. So they also help you out a lot with that too. Yeah.
I should also, sorry, those are really good sounds. But I should also mention Handshake is going to be on Canvas in the student portal. If you haven't already checked it out, it's where you can find internships, it's where you can find jobs. It's very useful. This is where employers are going to go if they're looking for students to hire. If you go just straight through the employment page, they might skip over you because they don't know if you're a student or not. Through Handshake, they absolutely do. Granted, some of these Handshake opportunities will make you go to the third-party sites, so Apple's website, NSF website, the National Science Foundation website, but a lot of them will go through Handshake directly. And so it's just beneficial for you to look on Handshake if you want to look for research opportunities, internship opportunities, and job opportunities.
Yeah, totally agree. Yeah, there's lots of really good stuff in Handshake, so make sure you get your resume on there for sure. Yeah. Oh, and I think that's also where you can register for the career fair, if I'm not mistaken. Yeah, for Sacramento State.
Some of them, yeah.
Some of them, yeah. Those career fairs here, they often post the registration on Handshake as well. So yeah.
Check your student emails. It's
yes,
very useful.
super important. Yeah. So yeah, if any further questions at all? No? All right, well, thank you guys for having me, and thank you all so much for listening.
All right, yeah. Just make sure you sign in right now, because in 15 minutes I can't sign anyone in anymore. Tons of food. If you want a sandwich for dinner, take one. You just need them gone. And yeah, what's up? Yeah, if there's any food left, take it. Yeah, look to your left, look to your right, introduce your name. Thank you, everyone. Woo!
Bye-bye.